Outreach Coordinator for the National Science Foundation EPSCoR program. And I also want to welcome you all for coming to this year's Science Within Society lecture series, which is our 4th year. And I must say, in 4 years, we have never had so many strange things happen. So I'm glad that we made it. I'm glad that this is queued up. And let's see, let me tell you a little bit about NSF EPSCoR, for those of you who aren't familiar with it. It is a federally mandated grant which offers money to 25 states that are considered underfunded in the research sciences, including the state of Montana. Our program primarily funds research at the UM campus, but also at the MSU campus, and we do a great deal of outreach. And an outreach project that's particularly near and dear to our hearts, of course, is the Science Within Society lecture series. So tonight, before introducing our lecturers, we'd like to thank our funding organizations, the National Science Foundation, the Montana Board of Research and Technology, for making this evening's lecture possible. As you know, this year's series focuses on climatic change, with our goal being to educate the Missoula community on global warming, the science, the policy, as well as the technological solutions, through the voices and perspectives of leading experts. Tonight's lecture by Dr. Steve Running will provide us with the scientific evidence surrounding climatic change. And Dr. Steve Running, as I bet most of you know, is a premier global warming scientist, as well as the director of the University of Montana Numerical Terradynamic Simulation Group, which is quite a mouthful. This research group was responsible for designing computer software that's used in satellites to chart seasonal patterns and changes in rain and vegetation growth. Additionally, Steve has been on multiple climatic change advisory groups, including the influential National Academy of Sciences Climate Research Committee. In short, Steve is the man when it comes to global warming research. But as some of you may have noticed, Steve is not here this evening. Unfortunately, Steve was called away to spend 4 days with the national media to educate them on the science and implications of climatic change. So this evening, instead of a live lecture, we will watch a pre-recorded lecture by Dr. Running. Needless to say, this is a small sacrifice for all of us here in the auditorium and a huge win for the nation as a whole to have his voice in the popular media, especially as the G8 summit approaches. I suppose that this must be the risk of lining up a lecturer who is the expert on a hot issue. But I promise that in all of our future lectures for the rest of the month, 1, we will not get locked out, 2, we'll be able to use the podium, and 3, that they will not be scooped up by the media. So, following the film, there'll be a question and answer period, and this Q&A period will be fielded by a rising star in the science of climatic change, Dr. Faith Ann Heitch. Is a member of Running's research group. Her research focuses on biosphere interactions on multiple scales, from a single tree to the entire globe. Her work uses both satellite data and computer models to estimate global vegetation productivity, and these estimates allow Running's group to determine how increasing atmospheric CO2 levels and global climatic change are impacting vegetation. We're honored to have Faith Ann here today, and we're thankful that you're all here as well. So what we'll do now is watch Dr. Running's lecture, and I'm just going to cue it up. There's an introduction of Steve Running, and he's already been introduced. And then we'll open up the floor following that, and you can have an opportunity for 15 or 20 minutes to ask Faith Ann questions regarding what you see in the film. So thanks for your patience.
In this talk, I make a point of avoiding showing you computer model results. Even though I've done a few computer models myself, I know that a lot of people, it's pretty easy to be skeptical about computer models. And so every slide I'll show you, with the exception of maybe 2, is directly measured data, field data. This is not computer modeling that I'm showing you of some distant future that may or may not happen. These are measurements that have been taken over the last decade, representing current trajectories and trends. And I think at the end we'll have some time to discuss the future holds, but I think it's really important in a topic like this that has so many skeptics to start with the facts. And really our job as scientists are to try to stay pretty apolitical, which is kind of hard to do right now, and look at the facts. And so we're gonna really spend our time here looking at what the scientists have produced for evidence. And I am on the Intergovernmental Panel of Climate Change. We are now writing the report that's due out in 2007. And so we're currently assembling all the evidence on this topic that you'll be reading about in the newspapers in about 2 years. So you're going to get a bit of an advanced look at what will be hitting the papers then. The 2000 IPCC report, the summary that you read most often in the public press is the one up here that I've highlighted, that the climate system is demonstrably changed, and that human activities are at least partly attributable. Now, the American Geophysical Union a couple years later had a similar summary statement, and these things go through a lot of what should I say, adversarial review. One of the things I've already learned about the IPCC report is every sentence I write is going to be scrutinized and cross-examined like some sort of a lawyer going after you. And so you really, if you try to write some speculation that you think might be true but with no evidence, you're in for a long battle. And so the IPCC reports are scrubbed of speculation very intensely by these adversarial reviews. So let's get on with it. How many of you have seen this figure before? The Mauna Loa CO2 record. This figure is on the entryway to the National Academy of Sciences in Washington, D.C., and has been called the single most important geophysical data set of the 20th century. How'd you like to, as a scientist, to have that under your belt? This guy actually lives down in Hamilton nowadays, C.D. Keeling. And he started this CO2 record in Mauna Loa. He put the site out there in 1957 so it would be away from local human influences. So it would really measure the CO2 of, you might say, the background atmosphere. And he dutifully measured that for probably a decade before they even started really getting serious about it. And now I don't have an electronic pointer. Does this have one of those too? Let's see. It does. This thing is, okay. The record started in 1957, and after 10 years they recognized it goes up every year. And this was the first, absolutely the first evidence that humanity was making a global impact. When you get up in an airplane and fly to another continent, it's kind of easy to think that we're pretty small and the Earth's pretty big. And yet this one graph showed that we were changing the entire chemistry of the entire global atmosphere. Now there's dozens of these stations around nowadays, down in the South Pole, and they're all over the place, and every one of them sees the same thing year after year after year. So this is unquestionable. We are changing the entire global atmospheric chemistry, and we have been for at least 40 years. My grad student showed me how to do that just a few weeks ago. So let's take a look now. That's, we think, the engine of change and the most commonly looked at greenhouse gas measure. Now let's look at the kind of climate trends we've actually seen in the last 50 to 100 years. Now this graph is only about a week old, and it's the mean surface temperature anomaly of the Earth for last year. And this shows for 2004, the areas that were pretty hot, and there's just about nowhere that was below the long-term average. Actually, the more important graph is the lower one, which is the running mean global air temperature since 1880. And so you see this poking along and drifting up. And one of the things that all of us in climate science keep wondering is it seems like something happened in the 1970s. Because I'm going to show you a number of other graphs that start a different trajectory starting in the early 70s. And we don't know what it was, but we continuously see a trajectory of this slope for a good long period of the century, and then all of a sudden, about 30 years ago, the acceleration of that trajectory. All right, looking a little more directly at air temperature trends for the U.S. over the last century, 01 to 98. The bigger the red dot, the more it warmed up, and the few blue dots is where it cooled down. So it did cool down in a few parts. What you see is all across the U.S. that we have warmed up by a degree to a degree and a half over the last 100 years. Now this one is a little harder to believe, but overall in the U.S. it's also gotten wetter. And as we sit and talk about ongoing droughts in the northern Rockies, it's kind of odd that the national statistics are showing the U.S. getting wetter overall. And I'll show you another graph on that a little later. And of course, you can still have sites and regions that don't follow the national trend. But overall, we are getting warmer and wetter, and that seems pretty clear over this last 100 years. All right, these next two graphs are the two modeling graphs, because one of the critical questions that we're trying to unravel now is how much of this is human causation. And you just can't, we don't have an experiment that we can run for the whole Earth to unravel that, so we have to use our computer models. And so when they run computer models that try to recreate the climate that I just showed you of the last century, the model bounces around in this gray area. Well, remember what I just said about this last 30 years where we've just veered up. This is what the observations sat around in the, you might say, the noise of the model runs until about the mid-70s. And then the climate took off. And the model, if you don't feed the model the increases in atmospheric CO2 and aerosols, then the model keeps chugging along the way it was. And only if you add the atmospheric CO2 increase and the sulfate aerosols to the model can you create this last 30 years of acceleration. And so at this time, this is about the best we can do at evaluating how much of the climate trend is human caused. And because we don't have a control Earth that we can run under a control environment, this is really the only way we can unravel this. And yet that, from a policy point of view, is certainly a critical part of the question. In fact, I'd say I've really seen the difference in just the last 2 or 3 years. When you go to Washington, D.C., virtually nobody, when you talk about this topic, disagrees that a warming trend is underway. So that's pretty much already been concluded by even the most vociferous contrarians. They say, yeah, it's getting warmer all right. What they've changed their question to now is, well, humans aren't causing it. And in fact, as they get nervous about the answer to that question, they have one last fallback, and I just figured this out in the last 6 months. The final fallback question will be, well, yeah, it's getting warmer, and yeah, we're causing it, but is it really hurting anything? And so their final question will be, and there's formal language that is part of the climate change conventions on, oh no, now I can't remember the exact words. It's on not degradation, human interference in the global climate. And negative human interference on the global climate is really the final threshold that they're going to demand scientists to illustrate before they decide that we ought to get serious in this. And so really it's pretty well, you're going to see in the rest of these slides that there's no doubt it's warming up. And so in these slides is where we've tried to unravel how much of this warm up is a natural variability of normal year-to-year trends of a natural climate versus how much is really a human perturbation. This slide isn't unrelated, but it's not totally related. I just had to put it in. I saw this a couple of months ago, and these are airplane contrails about a year ago that our MODIS satellite measured. Atlanta, Georgia sits somewhere right around there. And this gives you just a little bit of a glimpse at what the global airline traffic does to the aerosol loading of the atmosphere. And I'd never seen a figure like this, an image like this before. So one estimate is that these contrails alone may be worth a couple of tenths of a degree in aerosol loading and the resulting warming. That's a very hard number to come up with and justify, but you just look at that image and you kind of get the idea that there's a lot of airplanes up there. In fact, I remember hearing a statistic that O'Hare Airport out of Chicago had some unbelievable number, like 1 million flights a year. I thought, no, that can't be true. There can't be 1 million flights out of... And then I started adding up how many flights per day times 365, and you go, oh my God, that might be true. 1 million flights out of one airport? Have we gone crazy? Oh well, no, see, I was supposed to keep straight to the facts here, so let's get on to the facts again. This is the famous hockey stick graph. If you ever read about the hockey stick graph in climate change, this is it. And basically what a whole team of scientists from different fields have done is they've tried to assemble the various measures of the global temperatures over the last 1,000 years. All right? So we have, for the last couple hundred years, we have mercury thermometers. But then, and you can see where the variability gets bigger. We don't think the climate changed. This is about when mercury thermometers were invented. And so before that, they used things like tree ring records, things like sediment cores out of bogs. They go into these bogs and they drill these cores down, and they can look at things like pollen records, ice core records, and they infer in some very clever science what the temperatures were during those periods. And by the convergence of these estimates, they've estimated reasonably well what the global climate was for the last 1,000 years. And so this is what it looks like. And so we figure it bounced around in this envelope. I like to think of this as the natural envelope of variability. And it bounced around in there up until the industrial age started. So in the early 1900s, partly here we got better measurements. So this reduction of variability is part of it, a measurement artifact. But the real issue is that we're now about here. We have left the envelope of natural variability that's the Earth has operated under for the last 1,000 years. We've now pulled away from that. And I said I'd warn you whenever I talked about computer models. For the next 100 years, these are the trajectories that we expect. This is the worst case scenario, which is basically business as usual. What's a little creepy, though, is this is the best case scenario, which we aren't even close to even imagining yet. This is the best we think can happen. And look at how many degrees above the 1,000-year history of climate variability that the best case scenario for the next 100 years is. So we will probably end up somewhere around in here. And of course, this is where the Earth's been for the last 1,000 years. Okay, let's look at some of the Earth system responses that we've measured as a result of some of these climate trends. And you probably, a lot of you have seen this particular image. It's my backdrop. It's a satellite, it's a night satellite image of the lights of the Earth. And it's a real cool way of getting a sense of where all the population and all the energy is being used globally by just merely looking at the patterns of night lights around the world. Okay, one of the first things that you have to learn, and I have to confess that this only really sunk into me completely about 2 or 3 years ago. And I work on this all day, every day, and yet it never sunk in to me that well that climate trends come from the oceans. Because water is what has the real heat capacity of the Earth. Think it through this way. How many of you were here when St. Helens went off? Good number of you. Do you remember that after the ash cloud went over, about 10 days later it came around again? It was a perfect little tracer study of how long it takes the air to go around the Earth. And it shows that the atmosphere only has a 1 or 2 week memory. And it's gone all the way around the Earth and started back over. And so our weather, our day-to-day weather, comes from the atmosphere. And when you watch on TV at night what it's going to be like tomorrow, the forecast for tomorrow, that is really based on atmospheric measurements. When we start talking about climate, though, that goes for decades, the atmosphere is not where all the heat is. It's the ocean. And why it took me until 2 years ago, there was a key paper in Science that made this illustration. Now first, before I get to the key paper, this is what the oceans have done over the last 20 years. These are temperature anomalies of all the ocean basins around the Earth, and every one of them has gone up by 2 or 3 tenths of a degree. The ocean temperature, the water temperature itself. Now this is the paper that spun my top. You can go look at it, in 2001 in Science. And they worked out the heat content of the entire Earth system. And when I built this little table from the data, and when I saw that number, I finally got it. 90% of the heat content of the Earth system is in the water. The atmosphere is a total of 3%. All the glaciers, all the ice caps, all the snowpacks, all that only adds up to 5 or 6%. The oceans are 90% of the heat content. And so when we try to understand decadal trends of climate, it's now clear to us that we have to understand ocean dynamics, ocean circulation, and, let's see, let's go, the circulation part. You know, all this heat that is loaded in the tropics then is moved up into the higher latitudes by ocean circulation. The whole reason that you hear people talking about El Niños, you know what an El Niño actually is detected by? Ocean temperatures out by Tahiti. There's a bunch of buoys out here. And when those buoys, the temperature of those buoys goes up a few degrees, they announce that an El Niño is on the way. But it's all about ocean temperatures. And what we're seeing is that ocean temperatures are going up. In fact, in this paper, they added up that the oceans of the world had accumulated an additional 10 to the 22nd joules of energy. Now, how many of you out of physics remember what a joule is? I don't. It's some sort of watt per meter squared per something else. But I do know that 10 to the 22nd of anything is just immense. And that's the heat loading that has gone, the additional increment of heat loading that's gone into the oceans in the last, I think it was 40 years that they made that calculation. And that's what results in these sort of ocean temperature increases. All right, now if the oceans are warming up, it might be useful to look at how the Arctic ice caps are going. And for this, I have a quiz for us. How thick do you think the ice is at the North Pole?
7 feet.
Somebody's heard this lecture before, they're blowing it. I got to admit, when I first, I'm a terrestrial ecology guy, so I've never used to pay much attention to Arctic ice packs, and when I first started thinking about it, I just kind of offhand imagined, I don't know, it's probably 100 yards thick. Geez, it's cold up there and dark all the time. Well, some squealer told you that the polar ice cap at the North Pole is only about 5 feet thick. I mean, Georgetown Lake used to be about that thick by this time of year. But the critical part is we've been monitoring the thickness of the sea ice since about 1957, all up through the Arctic. And the reason we've been monitoring this ice thickness is due to the Navy nuclear submarines started going up under the ice cap, and they kind of needed to know how thick it was so they could come up once in a while. And so they took ice thickness measurements starting in the 50s that have continued to this day. And so this is a Navy data set, and it shows that the average ice thickness in the 60s and early 70s was about 3 meters. And in the last 30 years, that's shrunk by 40% in thickness. This paper only came out about 4 years ago, and there's 3 or 4 papers of everything I've read on this entire subject. And there's 3 or 4 papers that just take me by the neck, and this is one of them. Because these are millions of measurements from all across the Arctic by a clearly politically liberal, aggressive entity like the U.S. Navy, just looking for environmental hell to raise. And yet what they have found is this kind of reduction in the Arctic sea ice. Let's take another look at Arctic sea ice. We have a satellite, a microwave satellite that can see through clouds. It's been up since about 1979, and it's a pretty primitive satellite, but it does pretty well at just getting the aerial extent, area coverage of sea ice every year. And this is the trend since '79. An average trend of about 25,000 square kilometers per year loss of Arctic sea ice. Now, to give you a scale on that, Montana is about 376,000. So this is losing about the state of Montana per decade in Arctic sea ice, based on this satellite measure of aerial extent. You always hear about the glaciers around here, and my friend that is the climate scientist for glaciers says the estimate he gives publicly is that Glacier Park will be glacier-free by about 2040. And so we've got maybe 30 to 40 years left of glaciers in Glacier Park. Now, what's more significant, because what any one glacier or any one region does really isn't relevant to global change. No matter how good or bad or high or low any one place is, it's the global trend that we have to look at. Well, it turns out 95% of the glaciers on Earth are receding. There are 5% of them that are increasing, but 95% are receding. And this is kind of a clumsy graph, and I've looked for a better one, and I can't find a better one, but this has the main message. This is, since 1960, this line is the mass of the global glaciers. You add up the mass of every glacier on Earth, and this is the trajectory of mass of all the glaciers on Earth put together. And it's a quite continuous line down. And to just give you a picture or two, so we don't just look at graphs all night long, the South Fork Cascade Glacier over in North Cascades National Park. And I went up to this in 1968. And you see this from the late 20s, and you see how much all of this has now retreated in the last about 70 years in North Cascades. And of course, come on, Grinnell Glacier on Glacier Park, if you can see, this was the area that it covered in 1837. And this is 1993, and I don't even have an update of this graph. 1993 is a decade ago, so I suspect well, maybe that's it right there. And so we're clearly seeing this reduction in glacier mass right around here. And the more important point is 95% of the glaciers on Earth are seeing similar trends. It's interesting over the Alps in Europe. Like, they found that frozen guy in Austria a couple years ago. You remember reading about that? It was pretty. And Italy and Austria were fighting over who it was, because he's literally right on the border. And they don't exactly have a fence up there, because it was absolutely the tops of the mountains. Well, the reason things like that are coming to the surface is because the ice and snowpacks are receding all over in the Alps. And so he re-emerged after being down there for, what was it, 700 years they decided, something like that. Another look at the cryosphere. The Northern Hemisphere annual snow cover. And again, this is a simple satellite record. Luckily, one of the things a satellite can do best is tell the difference between snow and dirt. And your tax dollars at least have provided a satellite that, I mean, that's kind of a no-brainer, but you can see it's an important measurement. And what that measurement has found is the snow versus dirt ratio has decreased on the average of about 46,000 square kilometers per year over the same period. This is the same satellite that does the sea ice over this 20-year period. And so one of the things that's important when we look at warming trends is to not only look at temperature data. And that's why the cryosphere and monitoring snow and ice dynamics is probably our most important measure, because it gives you a full integrated area look at what temperatures are doing through the way they react in melting snow and ice. And so these are very important data sets. And the lucky thing is they're easy to measure. And so, yeah, I made a joke about snow versus dirt, but scientifically, it's important to be able to have measurements that are so clean and robust that they just can't be very wrong, because you just can't miss on this one very bad for tens of millions of square kilometers. And that isn't true of a lot of the other types of measurements we try to make. So clearly a trend of sea ice going down, clearly a trend of hemispheric snow cover going down over the last 20 years. Anybody here from Alaska? Few. I fear there usually is around Missoula. Your senator has gotten religion on this topic. Ted Stevens, despite what his other opinions on things might be, because of data like this. This is permafrost records from Fairbanks. And of course, up there, permafrost is a poor man's foundation for your house. Why bother pouring a bunch of concrete when you've got a free solid ice to build houses on? So forever, they just built structures on permafrost as a solid foundation. And that worked pretty well until it started to thaw. So you started seeing, these are temperatures centigrade, and by about the late 70s, in the summertime, the surface would start to thaw a little bit. Well, now look what we're up to. And this is 95. I can't find a newer graph for this. But even down to a meter depth, they're now close to thawing. And when I was in Fairbanks 3 or 4 years ago, there are houses that have had to be abandoned because part of the house just sunk down so far that it was just no longer safe to inhabit. And so this is a real issue. They build their roads on this permafrost, and then it melts, and the road turns into, what do we call it, spring breakup? Well, they have spring breakup for 8 months a year out there now. In fact, one of the things that they told me I had never thought of, you know how you get cars to Barrow, Alaska? I would have never thought of this. You drive them from Fairbanks up the haul road to Prudhoe Bay, you wait for the ocean to freeze, and then you drive them on an ice highway over to Barrow. About 400 miles. They actually lay out an ice highway every winter. And I don't think it has stoplights, but it does have little cones so you kind of stay on the plowed part. And that's how they've always gotten cars to Barrow, the cheap way. Well, the number of months a year that the ice highway will operate has gone down a whole bunch. And there's some sort of irony in this, that the oil and gas drillers in Prudhoe Bay are complaining that the winter isn't long enough for them to get out and do their work. And it absolutely, they're seeing a warming trend where just the way our loggers and people stay out of the woods during spring breakup mud. Well, it's the same issue up there, except the mud goes all summer long, and so they always tried to do their operations on frozen ground, and that duration of frozen ground is just getting shorter every year. Another curious data set. And of course, when we try to understand climate, we look for data sets that go back a long ways, and there aren't very many. But one of the other ones that's been around a long time are the dates when rivers freeze up in the winter and then break up in the spring. And of course, this had navigation and commercial importance, particularly
for a lot of cities. This is when your river froze up, you couldn't get supplies in until the boats could come in the next year. So they've been measuring this since 1845 in some of these cities. Now these are rivers all over the world, from Russia and Scandinavia, North America. This is a compilation. This was another paper in Science magazine about 2 years ago. So these are rivers all over the world, and if you just look at the basic trajectory of all these rivers, you see a general drift down of the rivers freezing up later in the fall, and a general drift up where they're breaking up earlier in the spring. And so, again, a sampling from all over the world, not just one point, and a general trajectory that you can see across all these data sets. And these are pretty accurate measures, too. Some of you might know of in Fairbanks, there's a big contest to guess when the river will break up, and they've geared up this system where when the river breaks and it drops some, well, you guys probably know exactly how it works. I've never been there. And everybody bets $50 or something like that, and whoever gets closest to when it actually melts gets a new pickup truck and $50,000 or something. It's big money. And so they've measured this pretty accurately because there is serious cash on the line. And so from a scientific point of view, that's important because it meant you have a measure with high precision that somebody's taken real care to get it right. And there aren't all that many measures that we have that go back 100 years with high precision. And river breakups are one of them. And so this is a particularly interesting data set for that. All right, intense storms and hurricanes. This is actually a point of big controversy right now. Florida got pounded good this fall, summer and fall, and so I was asked a number of times, is the number of big hurricanes increasing because of climate change? Our best answer is no. The theory suggests, the climate model theory suggests that it ought to, that you've got more energy from hotter water, hotter ocean temperatures, and that ought to propagate more hurricanes. But they have looked intensely at the record of hurricanes over the last 80 years, and there's so much variability that they can't really see a trend that it's increasing. And they're looking, because it's an important thing to know about. The Fortune 500 industry that first got dead serious about climate change science was the insurance industry. Oh yeah. I don't think the car industry has been very interested, but the insurance industry got very interested a decade ago because they wanted to understand whether probabilities of extreme storm damage were going up, and as I say, the theory suggested it ought to, and they wanted to know that. And so far it doesn't appear that hurricanes to the southeast coast of America are accelerating. And I think I read a paper that the same thing in Southeast Asia, the monsoon track, the same thing. They cannot detect any acceleration in either intensity or number of annual hurricanes. So doesn't seem like it. But sea level rise is clearly going up. Sea level rise is going up. Sea level is rising. And here again, we have records that go back a good long time, 60, 80 years. And you see just around the U.S. a clear trend of all these sites, except for Sitka. Tough part about measuring sea level from the land is you assume the land's stable. And what we're suspicious of is Sitka is still rebounding from the last glaciation. And we're only talking about a few centimeters here. And so that's the only interpretation we can give of Sitka going the other way. Now, one of the new NASA satellites is a sea level laser altimeter that can measure sea level to like a millimeter height. It's really pretty remarkable technology. So in the future, we're going to have a continuing measure of sea level from hopefully a more absolute point of reference from these satellites. And we're going to continue to watch this. But the sea level has certainly risen over the last 80 years by, something close to a foot. It's not getting this bad yet. But what we have seen, okay, so I said hurricanes aren't increasing, but and this paper was in the Bulletin of American Meteorological Society only about 9 months ago, so it's really quite new. They figured out, that the number of rainfall events in the continental U.S. that are what you'd call gully washers is little by little going up. Okay, they're defining more than 2 inches. How often does that happen here? I'm trying to remember the last time we got 2 inches in a day. But other parts of the country, it's pretty common. And you see that in the early part of the century, maybe 9-10% of the rain events would be of that extreme. And little by little, that appears to be sneaking up. So now it's more like 11%. So this is a little bit of evidence that, as the scientists like to say it, the hydrologic cycle is strengthening. Is the polite, unbiased statement we make. That more intense rainstorms are tending to get more intense in the continental U.S. Another totally different kind of metric, wildfires and fire acreage burn. This is for Canada. I actually can't put together a graph like this for the U.S. I've been trying for 2 months, and I can't do it. The data set doesn't seem to be amenable. But this is a paper just from 2 months ago, and from Canadians that show a very strong correlation between the area of fire burned per year, this line, and the observed temperatures for the area. And I won't even bother with the simulated temperature part. But they clearly, since 1920, and here again, seems like around 1970, something here again is a figure that we look at and we say, what the heck happened in 1970 something? Because we're seeing it from a variety of different types of measurements. All right, has the biosphere itself, has the living stuff shown us any response to these climate trends? Budburst in Aspen and Edmonton. It's a little bit of a funny slide to interpret, so I'll kind of speed interpret for you. Since 1900 to the present, the Aspen and Edmonton are now budding out in the spring about 3 weeks earlier. So the simple spring phenology is now 3 weeks earlier. This is a measure that we've also done by satellite, and we see at least a 2-week earlier spring bud burst over wide areas of the northern hemisphere. We've looked at the growing season length in Alaska has gone up about 2 weeks in the last 50 years. Frost-free season. And I remember as a kid, I'd see in the newspapers these articles about giant pumpkins being grown in Fairbanks. And then I'd get out a map and I'd look at, I lived in Seattle. Here's Seattle. Here's Fairbanks, way the heck up here. How in the heck were they growing 200-pound pumpkins? Or nowadays, they're like 600-pound steroid-driven pumpkins. And the thing you don't think about when you're a kid is when summer is up there, it's intense. It's 24 hours a day summer. So they, in one day, get 2 days worth of sun. And so they really can have quite a growing season for a short, intense period of time in the midsummer. And what this graph is showing is that frost-free period is clearly gone up a couple of weeks. And this was a dozen different sites around Alaska, not just Fairbanks. All right, let's look at the U.S. as a whole while we're talking about growing season. And this is where all the gardeners will stand up and cheer while the ski area owners hang their head in sorrow. The number of days per decade of increase in frost-free period, the way gardeners think of it, the time from last spring frost to first fall frost. Around here it's gone up 1.7 days per decade. So that's times 5. So it's been about 12 days increase in the frost-free period through the northern Rockies and Plains, a couple of weeks. Now, the part that, as climate scientists, we just can hardly relate to is this coastal stuff. I mean, this is almost a month longer frost-free period over there in California and Oregon, and you start vaguely remembering, hey, what about those ocean temperatures we were looking at just a few slides ago? And you can't help but think that that ocean warming has got to be rolling over into this data set here, because this is the margin along the ocean. Now what we've found, this is work out of my lab, is you put all this longer growing season stuff together, and the terrestrial biosphere appears to have increased in primary production by about 6% over the last 20 years. And so from the overall point of view of plant production, this climate warming you could call good news. It's certainly for the biosphere as a whole, the terrestrial biosphere appears to have enhanced productivity. Now when we go to the oceans, the news isn't quite so good. And the big issue that they follow is bleaching of coral reefs. And the reef ecologists quote a threshold of 85-degree ocean temperature, which is kind of hard to imagine in a February in Missoula. But a threshold of about 85 degrees where the corals really start to die, the algae in the coral dies off, and then that's what causes them to bleach out. Now they've detected this kind of bleaching and those kind of ocean temperatures all over the world. And I haven't seen a really definitive study on this yet, and I watch every week. And so I get a lot of anecdotal evidence of this, but not the kind of blockbuster papers like that ocean temperature one was, or like that Arctic sea ice was. So I'm still staying tuned for a really rigorous piece of science quantifying this, because I keep getting maps like this, and as I say, reports from all over. But I assume that if this is a real trend, we'll see a real rigorous paper on it soon. Now, what we do know is that the ocean productivity has gone down in the last 20 years. And it's kind of puzzling. Our lab found the terrestrial productivity has gone up. The ocean scientists, using much of the same satellite-based analyses that we do, have found the ocean productivity to go down. by about the same amount, but overall by about, I think it was 5%. And we found the terrestrial gone up 6%. I don't know what to make of that. This is just what they report. You can't ask questions yet. And so if you look basin by basin around the oceans, you do see that a few of the ocean basins have gone up a bit, but you see a real crash in places like the Antarctic. And I'm afraid I'm the wrong guy to tell you why. I'm a land guy, but it's a very clear signal there. A topic that we really don't know what to make of at the moment is, and I put this up for the kind of overall topic of human health. And we have things like SARS and hantavirus and things like that didn't seem like we had 20 years ago. And I get asked regularly if this is climate change triggered. And we really don't have good evidence that it is. And I particularly read a paper just a couple weeks ago that was very helpful to me on malaria. And it said 100 years ago there was malaria all around in the U.S. And so that it was public health and vaccinations that have driven those diseases into the tropics. It's not so much climate. So right now you might say that certainly the health scientists are keeping a very close watch on this, because human health is one of the big ones that kind of trumps everything else. If we really saw a serious human health issue ballooning out of control, that would get everybody's attention faster than most of the rest of this. But it's really hard to say that any of the changes in some of the human epidemiology that we're seeing are climate driven. They're probably driven by all sorts of other sociological factors. I got to say now, when I fly internationally, I just think I'm going to die. I just imagine all those airplanes just are a cesspool of foreign germs just flying all around me. It's awful. And no mask you can buy is good enough to save you. Just take it. Take the punishment. But you read some of these scenarios that with international air travel, if we ever blow out a big SARS epidemic in Hong Kong, it can be on every continent in under 48 hours. And that's the part that blows you away, is anything like this that could get out of control anywhere on Earth could propagate all around the world so fast we can't even imagine it just from international air flight. And so that's why there's a lot of focus on this, but we can't really blame any of these trends on climate that I've read. All right, let's see what's happening in Missoula lately. The average temperature since about 1950 has gone up about 2 degrees Fahrenheit, about 1 degree centigrade. This is the airport and the data from out at the airport. But this is the one that just spins our top. March has gone up 7 degrees in 50 years. So when the old timers say that winters used to be a lot tougher, a lot longer, they're not kidding. And I guess if you look outside right today, you start saying, there must be something to this. Winters don't last nearly as long as they used to. The good news is the heating costs, whether you believe it or not, are about 10% lower than they were in 1950. The bad news, if you have a season ticket at Snow Bowl, is that, and boy, this year, this graph really hits home hard. I've got 4 tickets sitting in my house that I'm not sure if they'll get used the way things are going. But we've lost in snowfall down in the valley bottom about a foot in annual snowfall over the last 50 years. And so you imagine that little Marshall Mountain was probably well, heck, my daughter skied there when they were small, and they're not all that old. So only about 20 years ago, Marshall was still a viable little ski area, and you can kind of see what finished it off. I didn't know until there was a PBS special, there was a little ski area outside of Butte that went under from lack of snow. The Butanians put this together in the 30s and skied. Oh, they all went up there and skied, and it finally went under in the mid-80s. And it was for lack of snow. So here we see again the number of days of frost per year have gone down by about 2 weeks, or so that frost-free period has expanded by about 2 weeks. This is absolutely consistent with that other graph I showed you, and so Missoula is right in the middle of what the national data set also showed. This is just a wider look at weather stations all around Idaho and Montana that Arnold Finklin put together. For all I know, Arnie might have shown up tonight. He was a Forest Service climatologist at the Fire Lab for decades, and so he sent me this graph a few years ago that clearly when you look at stations all around Idaho and Montana, you see a couple degree warming over the last 50 years also. Now this is the graph that hit me the hardest in the last 6 or 8 months. Paper came out that showed the snow water equivalent on April 1st all around the Pacific Northwest. And you see the red dots are a decrease of, most of these are 30 to 40% decrease in April 1st snow water equivalent over the last 50 years. And this isn't just 1 or 2 sites, is it? It's hundreds of sites around the Northwest. And what that then propagates is the timing of spring snowmelt has now accelerated by on the order of 2 to 3 weeks. And I'd have to say last winter was a dead ringer for this. We had a good winter of snowfall, had a good ski season, and then all of a sudden in mid-March, boom, it was just all gone in 2 weeks. And what these papers showed is this is a trend that has been developing and you might say accelerating across the Northwest now for decades. And this really quantifies that this isn't just 1 or 2 bad springs. This is the kind of overall trend that we need to pay attention to because it's real, it's been sustained for a long time, and it's an important part of our resource management. Okay, one other modeling slide, I think the last one. What we expect over the next 20 years. In about 20 years, we expect about 2 degrees Fahrenheit additional warming for the Northwest. This comes out of the Atmospheric Science Department at the University of Washington. In the next 40 years, expect about 4 degrees Fahrenheit of additional warming. So within maybe my lifetime, certainly all of yours, we're looking at doubling the warming that we've already experienced in the last 50 years. And so you kind of put this all together, and what do you see? We clearly see shorter, milder winters. And here we are living another one this winter. I keep figuring, okay, one of these winters we're going to have a really knockdown, freezing cold one like the old days to kind of tilt the balance back. And I keep waiting and waiting year after year, and it sure doesn't seem to be happening. So clearly that then manifests in earlier snowmelt, longer growing seasons, Makes me mad. When I first moved here in '79, I planted some apricot trees that promptly croaked. And I'll bet if I'd plant some again, they'd make it now. That early snowmelt really comes back to hit our stream flow in the late summer. And so all these years when our streams virtually run dry by August, we're probably in for more of that because the snowpack's going off earlier. When the growing season gets longer, the plants get all the water. And so the forests are actually stealing some of the water from the streams. And so that's good news for the forests, but it certainly doesn't help your stream flow any. And we're in for more of that. The drought and fire danger sure seems like it's accelerating. We seem to have had 5 of what they used to call 100-year fire years. We've now had 5 of them in 15, starting with the Yellowstone in '88. Now this figure we just put together a couple of days ago, because what I want to know most as a scientist is if it's clear that it's warming up, that to me it's real clear, the most essential part of evaluating how good or bad we're going to have it in Montana is whether enough extra water comes to balance out the higher temperatures. If it doesn't, we go down a spiral into a desert. If it does, then we end up with certainly a warmer climate, but just a warmer, milder, wetter climate that isn't nearly as catastrophic as the former. And so this is a graph of the Palmer Drought Index that has been mapped for the whole world for 100 years. And we homed in on the last 30 years for North America. And what this shows is all up through Canada, it's clearly warming faster than the amount of new water they're getting. So they're definitely drying out in Canada. And that maybe relates to that wildfire graph I showed a few back. What's kind of funny is that a fair bit of the U.S. overall is not, can I say aridifying? Is that a word? I guess I just made it up for tonight. Where it doesn't appear that the U.S. is aridifying too much. So in other words, as it's getting warmer, so far we're getting more precip, more rainfall to go with it. So that at least is going to help. There's some conspicuous problem areas like eastern Montana. And I'll bet every farmer and rancher in eastern Montana would say, yeah, that looks about right to me, because I know they really haven't done very well. But it's funny that through the Northwest, where this data set didn't show a real extreme increase in aridity. It's certainly getting warmer, but it's also getting wetter. I'm going to really keep working on this graph, because to me this is a pivotal part of understanding where our ecosystems are going to go. So let's just take a couple of, I tried to put down a couple of thoughts beyond the climate of some of the impacts that I might see around here. Certainly earlier crop planting dates. I notice wineries now being planted in the Rattlesnake. That's probably good news, isn't it? And so from the point of view of plant production, these climate change trends may end up being beneficial for Montana and the Northern Rockies. It appears, and the theory suggests that plant productivity will go up. Remember that as CO2 goes up, that also accelerates photosynthetic rates. But there's some other curious things I've thought about. We ought to have less deer and elk winter kill, because when the winter kill is worst is at the very end of the winter. And now with March warming up so fast, I guess all I can think is the Game Commission should liberalize the elk hunting rules and provide me with an automatic tag every year. It'd be a good start. But seriously, these suggest that things like winter kill of wild game might go down because winters are clearly not as tough for as long a time. Now, I'm curious, and somebody in here probably knows this answer. What happens to hibernating animals when it doesn't get cold enough to hibernate? Do they just walk up to Edmonton, or do they just say, I study plants, but I can't help but think that we're getting to a point where maybe some of the hibernating animals won't bother anymore. One of the things that we're looking at a lot is whether forest insect and disease epidemics might really be accelerated by these longer growing seasons, because that allows the insect life cycles to accelerate also. And so there's evidence in Alaska that the mountain pine beetles can get through 2 life cycles of summer, where they used to only be able to make it through 1. And so that's one of the ecosystem impacts that a number of people are looking at a lot. No doubt that stream ecology, this can't be good news. The water, the snowpack going off earlier, you're going to have lower flows, higher water temperature, lower dissolved oxygen. I can't remember that any of those are advantageous to any stream ecology I remember. And so I think we're going to be on a trend for stream ecosystems to just progressively be having a harder time of these longer, hotter summers. Now I have a few people. You know, I speak to a lot of groups on this that you might say are, what do I want to say, are hostile to the topic that I'm giving. And they invite me there on purpose, even though they hate me. I have a hard time understanding this, I guess. But, and a lot of them, I've heard a lot of attitude by some of these groups that I guess for the best way to summarize it is the U.S. is doing okay, screw everybody else. And so I put this slide in for anybody that might somehow have that kind of attitude. And this slide is the nitrous oxide emissions from 3 continents over the last 30 years. And of course, North America has stayed about constant. We're driving a lot more miles, but our cars are a lot cleaner. You remember the clunkers you drove in 1970 compared to what we have now. And so from the point of view of NOx emissions, our cars are pretty good. Europe is actually going down a fair bit, but look at Asia. Asia is just exploding. And China particularly sold 40%, is accelerating their annual car sales 40% per year. It's kind of interesting because I'm going to China tomorrow, and it's a fascinating place. Geez, that kind of reminds you of the international air. I'm part of the problem. I should stay home and ride my bike. The acceleration of car sales in China is just 40% per year. Economists can't even, their calculations can't even accelerate that fast. And so China is going to have this amazing situation within just a couple of more years where they're going to have lots of cars and nowhere to park them. I absolutely guarantee you in Beijing already there's nowhere to park a car in a lot of the city. And if at 40% per year for another 3 or 4 years, It's going to be really interesting. Now, what I really wonder is how they're going to host the Olympics in 2008. Because when I was there in October, they had a marathon race, and 2 guys died running a marathon. And of course, it came out in the papers they must have been out of shape. No. The pollution there is beyond what I can even imagine. And this graph really shows you the kind of acceleration that's going on of pollutant emission in Asia. And guess what? We're right in their tailpipe. Our satellite data clearly shows that the pollution clouds that come out of China come right across the Pacific and end up right here. So we can't run and hide on this one. This is a global problem, and every nation is going to have to chip into the solution. And if we think we can go it alone, the way Bush is trying to do with Kyoto right now, he's a fool. I mean, it's just ludicrous. It's just ludicrous. And we're going to be eating the emissions from Asia for as long as we're unwilling to deal credibly on this issue. And that graph right there shows you why. And, you know, this stops in 97. I'll bet this thing's up here right now. It's probably so far beyond the graph that we can't even get it on the page. And it's more coming, 40% per year. Think of that. Acceleration of car sales. And we all have a car, so we can't say that they don't get one. So it's quite an ethical dilemma for Americans. And we may not have to even make this choice. If you get a hold of National Geographic, this was just the June issue last year. And it was and the whole article was basically, well, the end of cheap oil is just about here anyway. And so whether we like it or not, and here comes around to international demand. And so the demand China has for oil is accelerating the day when the demand exceeds the supply for global oil supplies. The price will then go right up to the kind of $6 a gallon that it already is in Europe. It's already $6 a gallon in Europe, primarily from taxes, because they know better than to get hooked on cheap oil. And National Geographic suggests that this is right around the corner for America too. I'll let you read this one for yourself. And as you read that, think of how much any kind of environmental topic was in the presidential election this last year. Nothing. I don't remember either candidate saying a word on hardly any environmental issue through the whole election campaign. That's it. You've probably heard enough from me.
Okay, so we'll open up the floor to Faith Ann, and you're welcome to just field questions.
I think he got off easy and I get the hard part. Does anybody have any questions?
How is has fossil fuel use been measured? I'm sure it has. And how does it correlate with what we've seen in the 70s? Does it go through a similar upward?
A very similar trend.
Like
Yes, we've
fossil fuel
seen
use?
fossil fuel use correlates quite well with the increase in CO2 in the atmosphere. And that's the one thing, when we measure carbon around the world, that's the one thing we know, is how much we're burning. And there has been a dramatic exponential increase in the amount of energy in the form of fossil fuels being used since the 70s. Yes?
Just a few weeks ago on National Public Radio, I wasn't paying enough attention to the beginning, so I don't remember the scientific organization, but it was an international scientific organization that says that the human race has half a century left on this planet because we have so devastated our environment another half century. Can you comment on that?
That's definitely a doomsday view. I'd like to think that one of these days, really soon, we'd wake up. And I think the end of cheap oil is really going to drive us there. When we start having to pay $6 a gallon to drive our car down the road, we're going to start looking seriously at alternate sources of transportation. And I think that I have hope that scientists will be able to figure out new technologies along the way. And there's a talk in 2 weeks by, let me make sure I get his name right, David Merrill. And he's going to talk about the hopes associated with what we can do and what people are doing around the world to avoid these doomsday predictions. But certainly, if we continue in a business as usual sense, things aren't going to be looking good in at least probably my grandchildren's futures. Maybe not 50 years. I think that's a little extreme. The ocean circulation models have been predicting this for several years.
What they said is that they're not seeing the 3,000-foot descending columns of the heavily salinated water going down to the ocean floor, which are what drive the thermohaline circulation, and they're not seeing those this spring.
Right. We'll have to see, I guess, stay tuned and see if that's just this year or if that's an ongoing trend. But certainly the models predict that that's one of the things that could happen. And when we start messing with that and messing with the ocean currents, then we've really screwed up the climate. And we have no idea what would happen at that point. Yes.
Does everybody know where all the CO2 is going? I know it's absorbed in the trees and growth and bodies of water. How much can it sustain before it's overloaded?
That's a good question. We're researching that right now. We really don't know. We, if you add up all the sources and sinks of CO2, we can't quite account for everything. And we have this missing sink of carbon, and there was a really good article last year in National Geographic that discussed scientists around the world looking for this missing carbon. We think it's being taken up somewhere in North American forests, but as these forests mature, they're going to start slowing down their carbon uptake. And so they're not going to be able to be taking up as much carbon, and it's really going to depend on how fast temperatures rise, and because that'll increase photosynthesis. And if we have the water to go along with it, certainly our forests may be able to keep up these high production rates. But without the water to go along with it, the trees are just, they're not going to be able to make it. And that would definitely reduce the amount being absorbed. The ocean's absorbing about what we think it can absorb. It's kind of maxed out. We don't think it can absorb much more. So it's the vegetation and perhaps drilling deep holes and injecting CO2 down under the surface of the earth. And there's a few other technological things I've heard that they're trying to develop in order to get rid of the extra CO2. But we don't think forests are going to be able to sustain the kind of uptake that they've been sustaining thus far. Yes?
Warmer water temperatures can't hold as much gas, right?
Correct.
So if temperatures in water increase, then that maximum is also going to decrease. So therefore, the water, the ocean temperature, the ocean mass will not be able to hold as much CO2. Like the maximum it's holding now won't be the same at a higher temperature.
I'm not sure. I'm not an ocean scientist. I'm a land gal. I guess if Steve's a land guy, I'm a land gal. But I know that a lot of the CO2 tends to be held down in the deep, colder water. And the surface does uptake a certain amount, and I don't know how that's going to change as the temperatures warm in the ocean. Yes?
I thought it was interesting that you're saying in the mid-70s, the trends really started to go up. I didn't start thinking about this until midway through the section on Missoula. It didn't seem that held true. The graphs just went pretty much up in a straight line. Have you noticed any difference starting in the mid-70s for the figures in Missoula?
No. Nationally, yes, but at a local level, we don't see that. And that's one of the things that confuses the issue quite a bit, is why do we see this nationally, but we don't see it regionally, and what's really driving it?
Have you looked at other areas?
are people who are studying just the Pacific Northwest, and they're seeing very similar trends to what's going on here. A lot of the graphs that he showed were northern Washington, Idaho, and Montana, and that whole area seems to be responding similarly. Yes?
Recently, my attention has been drawn to an Austrian naturalist named Victor Schauerberger. Have you ever heard of him?
I haven't.
He wrote in the 1930s, and he predicted the current ecological disasters, including climate change, and pleaded for renewable energy. He wrote a book called Our Senseless Toil. I just ordered it.
Okay.
So, wondered if you knew about it.
I don't know about that book, but I know I was in school for 13 years getting my PhD. Didn't take 13 years to get the PhD, but starting from the beginning, 13 years. So my parents are thankful I finally graduated. But I kind of got, as I went along the way, I got maybe a third of the professors that taught me climate change is bunk. And the other 2/3 were like, or another third was like, well, we don't know, we're gonna wait. And then the final third was saying, it's true, we've been seeing it since the beginning of the century, we've seen these trends, we've needed to do something all along and we haven't done it. History tends to repeat itself. We didn't listen in the 30s. The current administration doesn't appear to be listening now, if I can say that. And until we really take a serious look and change the way we do things, we're going to continue along the same trajectory. That's the business as usual scenario that we hear about.
And what's the exact temperature, like say 50-year increase in the business as usual trajectory that you guys feel like the most current? You guys feel like, okay, 50 years from now we're seeing this much, this many degrees increase?
The graph that Steve showed shows about, I believe, a 4-degree increase over the next 50 years, and that's in 4 degrees centigrade. So that's what, 7 degrees Fahrenheit, 10 degrees Fahrenheit? So that's kind of what we anticipate. We're not anticipating a complete business as usual scenario.
Sure.
Or at least we're hoping.
Yeah.
So, yes.
Have you looked at the Hadley Center's modeling that they did online with everybody using shared computer modeling? Because that one, their top of the graph for 50 years is 14 degrees Fahrenheit.
Right, that would be the business as usual. I mean, if we change nothing and we keep accelerating our use of everything that we're doing now, and we're staying on that same trajectory, then we would see the 14-degree. I don't think we're going to be able to continue the rates of fossil fuel increased use that we've been able to sustain. And so I don't think really that we'd see that 14 degrees. I think maybe I'm just too optimistic, but I see much more closer to a 5-degree increase.
I guess I would reinforce that, just the limited resources and the price response that will occur is going to force changes in behavior, whether we're motivated by climate change concerns or not.
Exactly. And that's one of the things next week, Guy Dauncey is going to speak about the technology that's coming online, using more renewable resources and reducing our dependence. So I would defer technology-limited questions to him, because I don't do technology. I don't know technology. Yes?
Is this video available to anybody on the internet or?
It's not on the internet. It was.
It's from MCAT, and you could go in and burn a copy for $10. You just call in advance and let them know, and they can burn a copy and let them know it's the Steve running lecture. And you're also welcome to come to the NSF and EPSCoR office and to borrow it from us if you'd like, because we have 2 rooms.
In the future, is it going to be publicized that this was occurring, and maybe only in the next 2 lectures?
That's all.
It is being held right now.
Well, I know, but I found it very informative, and I felt like I've been to other seminars that have been forwarded on the national.
Oh, okay. Yeah, we do have, which I didn't mention in the haste of trying to get the movie to actually start. And we do, KUFM does air all of our lecture series, and so we do get full coverage for the state of Montana. And we have invited national organizations to cover our lecture series, and thus far they haven't been that interested. But Montanans are excited to get an infusion of science into their daily life through the public radio. Yes.
I think I heard you give the basis for an argument that we ought to cut all old growth forests in the northwest and stack the wood up so we can grow new trees.
Wouldn't the loggers love to hear that? No. I guess that's not quite the argument, because the trees that have been taking up the CO2 were under a cooler, slightly cooler, wetter climate, and they developed under that climate. The trees that we plant, if we cut down the old growth, we're going to change a lot of things in that area. Beyond climate change, we're going to change stream flows in the area, the way the snow falls, the moisture content. We could really make things worse by going down and cutting all these old growth forests. We might find that new forests don't grow back in those same areas. Or if they grow back, they're not going to grow at the same rate that the older forests did.
But if we have a wetter climate,
We don't know. I think precipitation, future precip, is the biggest uncertainty in the climate models at this point. Because right now, the way temperature has increased, precip is kept up. But if temperature continues to increase, is precip going to be able to match that? And we don't know about that.
I'd like to point out that not all of the water that is that the trees use comes as rain in the Pacific Northwest, and that includes this part of Montana. Fog, you've seen the ghost trees in the winter. You've seen the ice crystals that from the cold fog. That's all contributing to the water. And if we cut the trees down, that source of water is eliminated as far as getting to the soil. And in Washington, in particular, in the Cascade Range, there's some localized areas of desert because there's no trees to intercept precipitation, and regrowth is not occurring very readily.
And another thing that reminds me of is that the precip that's going up here is changing. We're getting less snow, and we're getting more rain. And rain falls, the trees catch it, or they don't catch it, it goes downhill, whereas the snow sticks around until it melts during the spring, which is the fastest time of growth for trees. So if the snow is not there, and they're just having to catch rain along the way, they may not be able to catch the rain at the time when they can really take advantage of it. Yes?
There's clear cutting relates greatly to that too. When I go to the recycling center and look down the Bitterroot, you can see the clear cuts. And those clear cuts do not hold snow. The snow goes off, the sun beats down, the snow goes off, and the water runs away. So the more clear cutting and more forestry, the less retention of water you have.
Certainly, yes.
Ethan, what are the implications of just in regards to drinking water on a global level, access to drinking water?
That is one of the big questions. Drinking water, potable water, for several reasons, has been decreasing. And part of that is due to just contamination of the water by other human activities. And I think that would be confounding the issue far more than anything I could conjecture. Are there any other questions? Thank you all very much for coming. And again, he's going on to a national stage and hopefully taking all this to the people who will take it then nationally.
What's the next lecture?
I'm not sure who he's speaking to because I was not privy to that information. The next lecture is by Guy Dauncey, and it's called The Sun and the Moon, Sustainable Energy at the End of the Age of Oil. And it will be next Thursday, June 23rd, Same time, same place?
Same time, same place, podium door open.